So, hello everyone. So let's start this presentation about a project that we have started at Amadeus that's called Cuba, and it's about system stability and anomaly detections around boats. So Cedric and I will run this presentation. We're working at Amadeus. So who have been using Amadeus software last week? Okay, let me ask the question in another way. Who took a plane to come to this conference? Here we are. So you have all used almost our software. We are a company that provides IT solutions for the travel industry, and we are a leader when it comes to traveling by plane. So a few numbers here. So this presentation will be divided in 3 parts. The first one, quick slides around distributed systems and stability. Then we'll see what we have already in the platform to enhance the stability of the system. And finally, we'll discuss this Cuba project. So when we have big systems like this one, I like to talk about the butterfly effect, because you all know this butterfly effect. When you have something very small happening, but weird, in one part of the system, it can really trigger some big chaos overall in the system and impacting all your clients. And this can be even worse depending on the load balancing strategy that you're using and how your application behave. For example, if we have an A application and a B application, if the A called the B only one time and you have only one instance failing, your client feels like he has a 20% failure rate on the system. But if your A layer needs to make multiple calls to the B layer, for example, an availability engine calling a pricing engine, and you have to call for multiple prices, you may have more than 25% failure rate, because only all the calls are distributed to all the B instances. In the industry, we have many quotes about failure is the norm, about stability of the system, how big they are and complex they are to operate. Today, I bring you one new quote from a French artist, Paul Cézanne. We live in a rainbow of chaos. Let's try to keep the rainbow and remove the chaos. And for that, we have some solutions. So let's talk about solutions. So, as I was explaining a few slides before, we may have to call another service several times. So here, an example with 6 instances of B. 1 out of 6 failure rate if you need to call B only 1 time per client request from A. Far more if you need to call them 6 times. Because if you need to call 6 times and you have round robin as a load balancing algorithm, then you will have a failure rate of 1. So, if you manage to do some proximity-based load balancing, and you're able to shard your system, and your algorithm that does the load balancing manage to contain the load balancing within this shard, you may reduce this failure rate for your user. So, one of the things that you can do is take availability zone as a shard of your system and try to contain all the collateral codes of your services inside the availability zone. More than that, it will be easier for you to spot the root cause of the problem in terms of locality. How do you do that? Well, today, natively in Kubernetes, you don't have solutions. There are already 2 issues open. The very first one here is about trying to load balance traffic to the same node if the service exists on that same node. The second one is trying to have load balancing topology aware to do what exactly I've presented on the previous slide. There is even a proposal for that in terms of implementation. And finally, even if there's nothing native in Kubernetes, if you're running a service mesh, and especially the one called Istio, that comes with a proxy that's called Envoy, and Envoy, this guy is availability zone aware. So you will be able, with a service mesh, to achieve what we have on the left. If you have applications that behave in a bad way when it comes to memory consumption, maybe you can use limits. If you have memory leaks, then this limit will prevent a container to eat all the resources of the system, and the kubelet will kill this container. So this can, in a way, protect you and improve stability, but fix the bug. Health checks in Kubernetes. If you type these keywords in the documentation, you will reach the page that talk about probes. We have two types of probes, liveness probe and readiness probe, different purposes. The first one will, in case of non-healthy container, kill the container. The second one will just remove the pod associated with the container from the service discovery. So the container will still be there, but will not receive any traffic. More than that, all the pod where the container is will not receive traffic, okay? It's an active health check that we have here. The activity is triggered by the kubelet on every container where the probes are defined. To define probes, you have three ways. The first one being TCP socket, trying to open a connection. The second one being send an HTTP request. Every 200 response will be okay. Everything else is non-healthy. And finally, you have another opportunities to use your own script. There are many parameters that you can use when you define the probes inside the pod definition. You can see, for example, the first one is initial delay, meaning that the kubelet will not challenge any container before this initial delay when the pod starts. A couple of advice associated to probes. Keep them simple, because I remember you that what we are trying to achieve here is having a stable system. If you introduce complexity somehow, you may introduce bugs, and when it comes to probes, this may be dramatic for your system. Okay? If you do bugs inside the probe, you can completely create a service outage. For example, keep it simple means don't try to check your external dependency. We are in a microservice environment, and you are not going to check if your dependencies are there or not, behaving correctly or not. This is their job also to do that. For example, if you reach the state where you have cycles, and this happens in big distributed systems, you may not be able to restart your system from scratch, even if you are checking your dependency chain. Another bad thing when checking dependency chain is that one pod may have different paths, let's say A, B, and AC. If the probe in A check the validity of the C, we may have a problem, because if the C is not healthy, then A turns non-healthy, but you have cut the AC, but at the same time you have cut the AB that was working correctly. The circuit breaker. So on the left side of the slide, the pattern circuit breaker that you may all know. It's a state machine here that we have, and we have either a closed circuit or an open circuit or half open, okay? How to achieve this in our Kubernetes environment? You can use a service mesh, either with Linkerd or Istio again. You will have a proxy being injected in front of, next to your, as a sidecar, sorry, inside your pods. And this will be the guy implementing the state machine. And let's take the example again of A and B. A is not connected anymore to all the B instance, or is not load balancing directly there. It's the proxy that is doing that now. And the proxy does an analysis of what's happening on the request, and especially on the response, right? If there is a timeout, if it's returning an error or something like that. And if one of the instances is not behaving correctly, then it removes it from the pool of potential endpoint for B. So it's the proxy that is doing this circuit breaker stuff. Keep this pattern in mind, because the Kubervisor project that we are presenting just after is doing this, but another level. Still, service mesh, and what they call the retry policy. So here again, we have this proxy that is doing an analysis of the response of a dependency, and that is able to trigger another call on another instance in case of error. So on the left side, you have the dashboard of Istio, and you see what's happening when you have a B instance failing, and that you activate the retry. So on the top, you have the success rate for the A, and at the bottom, you have the success and also, of course, the volume of request for the B. So you can see that when the retry is activated, the A finally returns only valid responses. And on the B side, we have an increase of traffic, but still a mix of success and error. So all these solutions that we have gone through quickly, you have seen that they are making local decision. I mean, it's always in the container. The probe is defined at container level inside the pod. With the service mesh, it's always the proxy that takes the responsibility to remove an endpoint or not. Okay? There's no orchestration of the activity of self-healing that is being done. And another important thing is that all the stuff is based on technical signals or KPIs. Memory consumption, connections, response time, timeout, analysis of the written code, and even the circuit breaker that needs to do layer 7 analysis, okay, is only linked to written code of HTTP value of the HTTP response. That means that if you have any other protocol than HTTP, you're not able to use this feature, even if you install the service mesh. It will do the TCP stuff only and not being able to do the analysis for the HTTP layer. So we introduce this project to try to overcome with this limitation. First, we want to take orchestrated decision, meaning that we don't want to look anymore at container or pod instance. We're going to act there, but we are going to take decision based on what's happening overall on the service. And also, we take decision trying to not make things worse. I mean, if you have all your instances that are failing, there's no point in taking any action on any of them. We wanted to take decision, being able to take decision based on any other signal than technical signal, and especially business signal. Okay, so you're going to see that in the demo after. We are using a business metric, and it will be the price of an air ticket. So the Cuba Advisor itself, the project is a controller that we are going to run in the Kubernetes cluster. Inside, it's made of two parts, the breaker and the activator. You remember the circuit breaker pattern, opening or closing the circuit. Basically, these two pieces are taking responsibility to change the state of the system each time. Breaking and reactivating some pods, you will see we will have different strategy for that. And to configure the system, we are going to use custom resource definition. So here is an example of this custom resource. So let's focus on the specification. The very first thing, which service are we monitoring and taking action on? Okay. The second part, the breaker. So here we have different value. Let's say the global setting for the breaker, where you say, I want to take action, but with some limit. I don't want to make things worse in case everything is failing. So you can define either in terms of count or percentage, the number of pods that you want to keep. It's a bit like a pod distribution budget, but at circuit breaker level. And then you have the strategy. I told you that there are multiple strategies. Here we see continuous value deviation. And how do you configure this strategy? We are going to reuse an external system that will provide us monitoring metrics, and here we're using Prometheus. We first define where to find Prometheus, and then you can inject the PromQL. This PromQL needs to be done in such a way that it returns, we will see that in the demo, a value that is 1 in case everything is fine, and then 0.5 if we have a 50% deviation, or 1.5, depends if it's up or down. Then you can say what is the deviation that you accept on this KPI, and the breaker, of course, will take action that if the metric returned by the PromQL exceeds this threshold. The activator, it's more simpler. You have to define the mode. We have 3 modes. The periodic, and for the periodic, you define the value in seconds. This is for the circuit breaker pattern when you go to alpha open again, okay? Trying to challenge again the pod or the instance against read traffic, and you put it either you break it again or you re-inject it again and so on. So this will do up and down for the pod when you use periodic. We'll see that in the demo. Another example. So here a different strategy for the breaker. Discrete value out of list, meaning that the promql will return you an array somehow, and you define what are the values that you accept as valid or the one that you don't want to accept, the bad values or the good values. And then internally the Kubervisor will do some computation, and I'm not sure if we have the ratio. No, we are missing one parameter, is the ratio of failure versus success that you have to define. And here for the activator part, we have a different strategy, retry and kill. Instead, it's a bit like periodic, but after a number of count of re-injection of the pod, you decide that, no, it's never going to be good again, so let's kill it. And finally, I think the last strategy we have in terms of breaker, it's custom. You can call any external service that will tell you, hey, this pod is not behaving correctly, or this set of pods is not behaving correctly. And all the Kubervisor controller will take actions in terms of removing the pod, re-injecting it, and applying the circuit breaker pattern. And here again, for the activator, we are doing periodic. But there is a last strategy that is not shown in this example for the activator. It's retry and pause. We'll see that in the demo. Instead of killing, it will put the pod aside and give you the opportunity to trigger some investigation on it. But when I say aside, that means that the pod still ran, but does not receive any traffic. So how does that work? So very simple. So we have a service that is having a selector, and so a set of pods associated to this service. Then you have a metric server. For us, it's Prometheus, that scraps the metrics. So technical metrics, functional metrics, whatever. Any KPI that you want. Of course, your pod needs to be instrumented for that. And then you have the Kubervisor controller, obviously. As a user of the system, you need to do two things. The first one is inject the definition, the CRD that we have just seen before. Okay? Then, once you have done that, the Kubervisor itself is running. Now everything is fine. It can manage the pod that are associated with the service and query Prometheus with the promql that you have defined. And start to apply the strategy. But nothing is going to happen. You are in a kind of dry run mode here for the Kubervisor. Why? Because if you want to go for a live and taking real action in terms of service discovery and ejecting some pods, you have to append one thing to the selector, that is the label associated to Kubervisor traffic equal yes. And at that time, if a pod is considered non-healthy according to the query that you have done, Kubervisor will change automatically the label value, and the pod will be removed from the service discovery. So, demo time. Cedric is going to run that. He's the brave guy. Yeah. I'm just talking.
Live demo, so it will maybe fail. So, as said David during the introduction, Amadeus is a company working in the travel industry. So let's do the demo with flight search price. So these services will return 3 best price for an origin destination city for the current day. If we take the same slide as the previous slide, so we have pricer services with 4 different pods running, and we are using Prometheus to scrap some business metrics. So the price for each returned by each pods when you receive a request. So let's go live. So let's see first what we have already running in our cluster. So we use Minikube for the demo. Here we can see, I hope, that we have 4 different pods for our services, so the pricer services. Then we have our Kubervisor pods here, so it's a controller that is running. And then we have Prometheus and Grafana running thanks to the Prometheus operator. I will start to inject some traffic. So this is the price returned by our services, and if you want to see how it looks like. Let's come back here. So you provide, it's a REST services, you provide the origin and the destination, and it will return some price for it, so 3 price, as I say. We created also a dashboard to show this information. So let's maybe a bit bigger. So the first line is the business information that we have, so the number of requests received by each pod. And for the origin destination, this is what we see here, and also the average price returned by each pod for the origin destination. On the bottom of this Grafana dashboard, we will see after some other metric returned this time by the Kubervisor controller. So let's come back to the terminal. So here we see we have only the pods of our application, and what is will be interesting to look at is the labels that will be added automatically and updated by Kubervisor. So first thing that we need to do to use Kubervisor is first create the Kubervisor services. And this is the first configuration that we'll use. So first you provide the name of the service. This is the services attached to our pods. And then the breaker configuration. So we use Prometheus. So this is the URI to the Prometheus instance. And then we have the promql request here. So if we copy paste this promql and go to Prometheus, and what we see.
Yeah, we have so we are running the continuous value deviation strategy. So your promql query have to return a value that is 1 when there's no deviation, okay? And it have to group that by pod. So this is what we are doing here. If you look at it precisely, you can see that we are trying to get over 30 seconds the average price value that is being returned against the total average, the average of all the set of pods. What is interesting also in this query is this end clause that we have here that allow us to exclude from the analysis any pod that is not receiving enough traffic. Okay, we are making statistics. Statistics are good on big numbers. So if a pod that has just started or not receiving any traffic is not interesting for the analysis. So here is an example of query. I'm pretty sure that you have all promqers and there are experts here that will find better way of achieving this. But the important thing is that we have a value here, float value return close to 1 when there's no problem. And we'll see later on that this value is going to change.
Okay. Thank you, David. So let's create this Kubervisor service. And what we can see on the top of the screen is that we have 2 new labels added on each pod. So we have the name of the Kubervisor service, and then we have the traffic label here, equal yes. So it means that for the moment, Kubervisor thinks that all pods are healthy. So since we are good coder, we don't have any anomaly in our pod, so let's inject it. So first thing that I done just before is that, okay, we added modify the label selector on the services in order to have now, we can see here, the new selector labels, that is traffic equal yes. And now let's inject some anomaly in one of the pods. So for that, as we can see here, the price of one pod returns 0. Maybe it is very good for the user. We can travel for free, but we will have some trouble after that. We also implemented quickly a plugin for kubectl in order to see the status of our custom resource here. And what we can see is that we have currently 1 pod breaked. This means that we have traffic equal no here. And since I didn't comment it, but we choose first the periodic modes for the activator, every 15 seconds the pod will come back on the services, and so the traffic we will see as again some error appear here. Yes, so it come back to yes, so we have again error, and this is we done this mode as periodic. It's because sometimes you have an anomaly because a pod is overloaded because the node maybe is not healthy. So by removing these pods during a period of 50 seconds, maybe the load of these pods will decrease and it will become back healthy thanks to that. In our case, it's not the case. If we come back here, what we can see is that these pods now always return 0 when he receives traffic, and also what we can see is that this pod receives less traffic from the other, and the other pod have an increase of traffic because they need to serve the request, more requests than before. So now what we can see here also is the metrics returned by Kubervisor, and we can see the pattern, okay, yes and no, and this level of request corresponds to the half open pattern defined by the circuit breaker. And here we can see that sometimes it's 0, 1, 0, 1 at the break part. So for our case, that the pod is not able to come back normal, what we will do, we will change the activator method. So first I will delete the pods that have an issue, and we will update the configuration. So this time what we will put is retry and kill method for the activator. For the breaker part, it's still the same. We choose the same period, 15 seconds, and with the max retry count equal to 1, it means that Kubervisor will try, if a pod have an anomaly, will try first to remove it and to come back behind the service. But at the second issue, it will kill the pod. So let's apply this update on our Kubervisor service and inject again some anomaly in one of the pods.
So you're going to see that some zero are going to fly for a bit of time. It's because of the range query that we have done over 30 seconds. Okay?
So yeah, so here we can see that we have the pod with traffic equal no. It should come back once at yes, and after we will see that this pod will be terminated and a new pod will be created by the replica set controller. So again, we are yes and no, and what we should see, it's terminating, so the pod was deleted, a new pod was created. So thanks to that, we was able to retry a bit to have a healthy pod, but after some retry, we kill it, and Kubervisor take the rest to come back to normal by creating a new pod. So this is great for the quality of service that we want to put behind the services, but for investigating, it's not very practical because we don't have anymore the pod instance to look at it. That's why we have the last configuration for activator is the retry and pause. So this time we added a new parameter, is the max pause count, and this is the number of pods that Kubervisor can put in pause mode for your services. So let's apply this update on the Kubervisor service. And again, create some faulty error in one pod. So again, some price go to 0. And we will see like traffic equal no once, and the second it will come back to yes, and after it will go in another value that is pause. So yes, and pause. For the moment, the demo is okay. It's good.
And it's close to the end, so
yeah. So I can smile. The traffic, we can see that we don't have any more error. We still have the pods for investigation, and so maybe you can create some alerts thanks to this label and everything. the team responsible of the application will receive to say, hey, maybe you have something to investigate. We save your ass by removing these pods, but it's not done for you. And so let's see. Yeah, so let's think that we want to show you is that how Kubervisor is able to know how many counts is done for each retry on the pods. So for that, we use annotation on the pods. We have two annotations. We have the retry count, so equal to, because first time it's the first try, and the second value, the second iteration is when it was put in pause. And we have also the last time that the pod was break. And like this, for investigation, is cool because you can look at the trace at this average time or the request that receives these pods. So it helps you. To investigate the issue, and also why we use annotation is like this: the Kubervisor controller is completely stateless. We can restart it, load a new version. All the information is inside the custom resource or directly on the pod and the services. So that's it for the demo. Just a few slides before questions. So first things that here we want to show you is that we are using really the pattern of controller in Kubernetes. So we have a controller part that is watching events on the Kubernetes service custom resource, but also on the pods and services that is associated to this Kubernetes service. Inside this controller, we have two main parts: the activator and the breaker part. This is very thanks to that we are able to add some new feature easily. And one of the possibilities that we have is to change the anomaly detector that we use. So in our example, we use Prometheus, but thanks to this interface part here, we are able to use other metrics systems that can be used in your company, like a private solution that you already have.
So, as you have seen in the demonstration, in the demo, the Kubervisor is putting some labels and annotation on each pod when it needs to break it. What is cool with that is that maybe this can be reused by any other controller or part of the system. For example, in Amadeus, we are looking at how to leverage this system when we are doing canary deployment. Because your canary deployer, when it deploys the canary, can look at the annotation associated to the canary instance, and if it figures out that the Kubervisor is often removing this pod from the traffic and the service discovery, maybe there's no point in continuing the deployment. Okay? So canary deployment is just an example. You probably already have some ideas how you could use that. So some key takeaway for this presentation. There are many ways of improving the stability of the system. We have listed some at the beginning of this presentation, and we are proposing here another way. This way allows you to use your business KPI, if you have any. It leverages any external monitoring system like Prometheus or any other that you would like, and provide you some automation to do some kind of circuit breaking on top of Kubernetes concepts. It's based on standard stuff, CRD, PromQL here, but services and pod. It's clearly extendable, not only because it puts labels and annotation, but also the architecture itself of the software is there to allow you to plug some new strategy, code strategy if you want, inside directly the Kubervisor. We are open sourcing this tool. We, of course, are happy to receive any comments, so please check out, try it, break it, post issues, and call us. We have maybe the time to take one question. At least one of the questions is answered on that slide. If you're wondering why it's called Kubervisor, you have the answer.
Yeah, and you have the links to the repository on top of this slide.
Yeah. So maybe one question. We have time for one question.
what you showed here, it's very interesting actually. But probably I missed something, or didn't get that. You are not cutting the traffic. You are changing the label, and you hook this label to some external, I don't know, Istio or Envoy or something like that.
As you said, we are changing the label, and as such, we are reusing the native service discovery mechanism of Kubernetes that is associating a pod to a service thanks to a label selector. We have changed the label selector, extending the label selector with traffic equal yes. And we are manipulating the traffic equal yes or no or pause on the pod. Changing this value will remove the pod from the service discovery, but not from the replication controller or the replica set. Okay? Replication controller if you're using OpenShift, replica set in Cube. So thank you, and
thank you.
Please use the software.